Alright, you might as well stretch out before we do this problem. There's nothing especially hard about it, especially since we're going to use some of the shortcuts we had from the previous video about when you have more than two reactants. But I added in, just for fun, a last step there to see what we could do. Alright, same basic process. It's like a single elimination tournament. We got to get moles first. Let's jump right in. 200 grams of each reactant given, so I've got 200 grams of our NaCl, 200 grams of the sulfuric acid, H2SO4, and 200 grams, of the manganese dioxide, which happens to be an oxidizing agent and works pretty well at decomposing peroxide. We're going to divide by the molar masses. That's 58.44 grams per mole, 98.09 grams per mole, and 86.94 grams per mole. And this will get us our half amounts that we're going to start with to do our comparison. In the case of the NaCl, we have 3.42 moles. In the H2SO4, we have 2.04 moles. And in the case of the MnO2, we have 2.30 moles. And I'm not going to do a total shortcut. I'm going to bring back this previous video's sheet. In the previous video, we said we could take whatever we identified as our limiting reactant in advance and do all the comparisons right off the bat. I'm going to split it into two steps, and I'll do the reactants for one, and then I'll do the products for a second comparison. But this part right here is going to look the same. We've already done essentially this part, so we're still going to have to do this. So in short, got to get moles, got to have a balanced chemical equation. I'm going to do that comparison to our limiting reactant to get amount excess, and then I'm going to do that comparison to our limiting reactant to get a theoretical yield. If you didn't watch the last video, you're probably better off. I'm going to pretend I have a bracket set up here, and we'll just seed it as it is. If you watched the last video, you know what I'm talking about. If you didn't watch the last video, just ignore what's about to happen. It doesn't matter who starts this tournament out, but I just want to set this up because it's important that we predict a winner. Okay? And this one's a little easier than the previous video. By moles, I'm supposed to have 4 times as much NaCl as manganese dioxide. I'm supposed to have twice as much NaCl as H2SO4, and I'm supposed to have twice as much H2SO4 as MnO2. So these coefficients give us the ratio of moles we're going to need. So right off the bat, I'm going to say, all right, I got 2.3 moles of manganese dioxide. I need 4 times as much NaCl. Do I have 4 times as much NaCl? No. In fact, I don't even have twice as much NaCl. So NaCl is limiting compared to MnO2. Right off the bat, we know. And then I'm going to look at the H2SO4 versus the NaCl. And I'll say, all right, I'm supposed to have twice as much NaCl as H2SO4. It's a 4:2, a 2:1 ratio. Twice as much NaCl as H2SO4. Do I have twice as much NaCl? No. So NaCl is my limiting reactant. All right? So I cheated. I guess I didn't seed this part of the bracket. Oh yeah, good. Faked it. NaCl wins, and NaCl wins. That's our limiting reactant. You didn't have to do that. If you have no idea what I'm talking about, then pretend that never happened, and let's do some comparing. I'm going to compare my limiting reactant to my excess reactants, and this ended up being our excess reactants. The comparison has to be versus the NaCl, so let's just do all that at once. I have 3.42 moles of the NaCl, and as we set this dimensional analysis up, I know that for every 4 moles of NaCl, I'm going to have, I'm going to just try and pick some colors that work here, 2 moles H2SO4, and we're going to have 1 mole of manganese dioxide. That gives me 1.71 moles of H2SO4 that I'm going to need. And it gives me 0.856 moles of the manganese dioxide that I'm going to need. All right, that's what I need of those. That's what I have of those, and we're going to do a comparison there. And I want to try and match those up. So I have these three amounts, and I'm going to compare these for my excess to get our amount excess. So we needed our needs compared to the limiting to find our amount excess. And if those words sound a little weird, this is like my 6th video today. My eyes are bleeding. Our amount excess, same as always, we're going to do have minus need. It's just that with 3 reactants, 2 of them have to be excess, and 1 of them is going to be limiting. We have 2.04 moles of sulfuric acid, and we're going to subtract the 1.71 moles of sulfuric acid. We have 2.30 moles of manganese dioxide, and we're going to subtract our 0.856 moles of manganese dioxide. And those numbers give us 0.33 moles of H2SO4 and 1.44 moles of MnO2. We need to turn that into masses. They didn't say it, but we'll declare grams are more useful in terms of us understanding the numbers anyway. We'll multiply by our 9809 grams per mole, and we'll multiply by our 8694 grams per mole. I don't really like where this is going on the page, but I'm committed. We end up with 32.4 grams of H2SO4 excess, and we end up with 126 grams of MnO2 manganese dioxide excess. And I guess it's worth noting that these numbers match the yellow numbers, and that's what got us our amount excess. All right, stretch it out. We need to get a theoretical yield using our limiting reactant. That's our NaCl. I don't really see a bad place to put it, so we'll just try and sneak that in right here where the tape is. Long story. Our limiting reactant was the NaCl. We have 3.42 grams of it. Sorry, 3.42 moles of NaCl. And that's going to be the basis for our dimensional analysis. We know from our balanced chemical equation that for every 4 moles NaCl, we're looking at four products. Geez, I'm going to need another color here. How about hot pink? We're looking at 2 moles of sodium sulfate, and that's going to give us 1.71 moles of sodium sulfate. We can multiply by the molar mass, which is 142.05, and that gives us 243.1 grams of sodium sulfate, theoretically. Ugh. All right, we have 1 mole of manganese chloride. That's going to give us 0.856 moles of manganese chloride. Oops, I knew there was a 2 missing there. 2 moles of manganese chloride, sorry, 0.856 moles of manganese chloride. We'll multiply by its molar mass, which is 125.84 grams per mole. And that's going to give us 107.7. I don't know if that's plenty visible. All right. We've also got the water, so 2 moles of H2O. I thought the last color was going to be hard to see, but we just upped the bar on that. And that gives us 1.71 moles of H2O. We'll multiply that by our 18.02 grams per mole, and that'll put us at 30.8 grams of water. As if the videos weren't hard enough to see already, I've got this ghost pink pen. Alright. And last but not least, we've got the chlorine, 1 mole of chlorine. So we end up with 0.856 moles of chlorine. We're going to multiply by its molar mass, which is 70.90 grams per mole. And we end up with here 60.7 grams of chlorine gas. So this is our theoretical yield. These are the things we're expecting to see in the end. I don't really have a good way to highlight on this packing tape, but this is our theoretical yield. And we only did 1 comparison here, well, 2 in 1 box, and 4 comparisons there, just to the products. Maybe I can highlight it with this blue pen. Alright, now let's talk about what the rest of the problem says. The reaction takes place, we got a bunch of stuff floating around in solution, and we have some excess stuff floating around in solution. We're going to dump in some barium nitrate, see what happens. We're theoretically going to precipitate out some barium sulfate, although I ignored this excess H2SO4 when I made this problem up, so I will continue to ignore it as we solve the problem. Alright, we've got barium nitrate, and we've got sodium sulfate. And we're going to add those together. Alright, we end up with a completed balanced chemical equation that looks like that. We can split it up, like this is double replacement. We can set up a complete ionic to get a net ionic equation and all these other words. The actual reaction that's taking place is the barium ions and the sulfate ions, giving the insoluble barium sulfate. That is what's going on in pink. So this 351 grams that it says right there applies to our barium sulfate. And I've got the molar mass of barium sulfate. It's 233.4. I calculated that in advance. Green. There we go. 233.4 grams per mole. All right. So we have an amount of this, we just need to like backtrack to this and see how things go. We had a theoretical yield of sodium sulfate as 243.1 grams. The question is, how much barium sulfate would that much sodium sulfate have made? And we'll have to work our stoichiometry to find out. We need to take our 350.1 grams and turn it into moles. We know how to do that. We'll take our 350.1 grams, that's our barium sulfate. We're going to divide by the molar mass, which was 233.4. And we get a number there, and that number happens to be 1.5 moles of BaSO4. Now when I did this on separate paper, I actually set it up as one continuous dimensional analysis problem, but I'll just pick up as if I had set it up right there. We've got 1.50 moles BaSO4, and via dimensional analysis we need to somehow get back to Na2SO4. I know that for every 1 BaSO4, there was 1 mole of sulfate ions. That's what it says right there. And that's our unifying item there. For every 1 mole of sulfate ions, I have 1 mole of sodium sulfate. And once we know that, we know the molar mass of sodium sulfate. For every 1 mole of sodium sulfate, there's 142.05 grams of sodium sulfate. And if you follow the cancellation through, moles of barium sulfate goes away, moles of sulfate goes away, moles of sodium sulfate goes away, and we're left with grams of sodium sulfate. And that number happens to be 213.1 grams. And what that number is, it is our actual yield. And we know it's our actual yield because it turned into that. The sodium ions were spectators, we saw that, and all of our sulfates turn into barium sulfate, all right? And that is this thing right there. We are asked for a percent yield, and the way we calculate percent yield is the actual over the theoretical times 100. In this case, our percent yield is going to be our actual yield, which is 213.1 grams of sodium sulfate. And boy, is it helpful to label stuff, because I know that I need to turn that grams of sodium sulfate from the 243.1 grams of sodium sulfate. Multiply by 100, we end up with an 87.6% yield. And if you're wondering why I would take such a bizarro approach to get from point A to point B on this problem, it's very common. Like, we do a lab in my AP class at the end of the year where we make alum, potassium aluminum sulfate. And one of the last steps is checking the percent sulfate by precipitating it out with barium. So what I'm saying here, and we had to ignore that sulfuric acid because that was extra sulfate in the solution. So we'll pretend that never happened, and I just continued on my merry way. But you dump in a bunch of barium nitrate, enough that you know it forces the equilibrium all the way this way. You measure your mass of barium sulfate, and that tells you how much sulfate you had to begin with. All right. So this is a soluble product. We can dump some stuff in to make an insoluble product, and we know the stoichiometry to relate them. So it's a pretty slick way of working backwards to get a percent yield or a percent sulfate content or something like that. This is the last non-solution stoic problem I'm going to do. I'm glad to be done, and I think we've pretty much covered all the bases that might come up.